Okay, so we're getting into our next conservation law, which is going to be momentum. And on the way to momentum, we got to stop off and talk about impulse. Now, when we talk about work, we know that work, how we've explained it, is to say it's the integral of f dx. Okay, and so if we've got some kind of force that's a function of distance, okay, whatever, okay, we can look at the area underneath here, and that's going to tell us what the work value is. And then the work value is equal to the change in kinetic energy. Okay, so something you got to grill into your head, make sure it stays there, is force distance, kinetic energy. Now, impulse, okay, which we'll use an I, is similar with the dt. Okay, and so we might have something here, but it's a function of time. All right, and so the area under that curve, that's our impulse instead of our work function. And the impulse is equal to a change in momentum. Okay, so they're very similar ideas and they're used in similar ways. So everything you've kind of learned about work, all those ideas, they pretty much apply straight over with kinetic energy. Now, one thing that is different, however, is that impulse is a vector quantity. Okay. Energy and work are both scalar quantities, but impulse is a vector quantity. And if you think about it, since we're saying that momentum is mv, all right, the velocity is a vector quantity and m, the mass, m, is a scalar. So that just sort of seems to make sense. Okay, so in this particular problem here, 15.4, there's some force, all right, described by the graph, okay, and that's going to propel the car forward, all right, so that ultimately comes from static friction, all right, so static friction is propelling the car, making it go forward. And it says determine the speed when t equals 10 seconds or 6 seconds. And so what we really have to do here is just figure out our area right here. Okay. All right. So let's do that real quick. So this first one, let me call this area 1, this area 2. So area 1 is just 1/2 height times base. Okay, so that's 6. And area 2, it's a rectangle. It's 6 by 4, so that's 24. So together that is 32. 30. Sorry about that. 30. Now what are my units there? Okay, well, it's Newton seconds. Okay. But nobody does that. Okay, nobody does that. Come back down here. It's momentum. It's momentum. And so we don't say Newton seconds. We say kilogram meters per second. All right. Now that's not any, that may not be an improvement really, but there it is. Okay. And then to work this one out, then once you've got this value for 30, then that's going to be equal to your delta P. And so it's all going to be X. So P final minus P initial. And we're starting from rest. So that term is 0. So take your 30 and set it equal to MV. And voila, your answer is going to pop right on out of there. Okay. Just like that. So what we're going to do now is we're going to look at another video or another situation. This is going to be actually 15-1, but it's going to allow us to sort of see impulse as a vector quantity. Okay, so let's jump and do that. Let me see here. There it is. Okay, so we've got this ball and it's coming down and it hits the wall and then it bounces off. So it comes in at 25, it goes off at 10. So it has slowed down and it has changed direction. Okay, so some kind of force had to happen to this thing. So the way we think through this is by starting with considering what we'll call here P initial Y, and we've got P initial X. And then sometime later, we've got P final X and P final Y. Okay, so there's an I impulse, there's a Y impulse and there's an X impulse. And so the Y impulse is going to be P final Y minus P final X. And then the impulse in the horizontal direction, P final X minus P final Y. Okay. Now, once we have those two things here, this particular question, it says determine the magnitude of the impulse. Okay. So we've seen that clue before, magnitude of something or other. Anytime you see magnitude of something or other, you need to automatically jump to knowing that you're going to have to do something like this. You're going to Pythagorize something. Okay, so if we get our IX and our IY, boom, then we've got it just like that. Okay, so what we need is we need to get PFY and PFX, PIY and PIX. Okay, so pick a slightly different color here. All right, so the way I like to do this is to go back to sort of our original way of thinking about vectors, which is a scalar, or to use the bracket notation. I'm a fan of bracket notation, as you know. So I need a magnitude term. So I need the mass and I need the velocity. Okay, so this is going to be 0.5 kilograms times the velocity, which is 25 meters per second. All right, and then I'm going to put this onto some bracket notation. So I've got cosine 45 minus sine 45. Okay, so there's my vector form for the final momentum there. And similarly, I'm sorry, guys, that is not the final. That is the initial. There we go. Fix that right up. The final, we're going to have 0.5 kilograms on 10 meters per second. Okay, and then what we're going to have is our angle cosine 30 degrees and sine 30 degrees. Okay, be careful. Make sure you remember to put that one there as negative because it's a downward component. Okay, it's easy to forget that. Now, once you've done that, now you're in good shape because you've got this times this gives you your initial x component here. Okay, this times this gives you your initial y component. Okay, you see how it works there. So pass that into the brackets, find your components there, and then just subtract them. That gets you your impulse, and from there you get your magnitude. You Pythagorize that baby, and you'll be good to go. Okay. Now, in a case like this, why might we care? Well, it's because there's going to be a normal force here. Okay, and we might want to know something about that normal force. This impulse here is going to get us that information if we wanted it, because that's going to be our F dt. Okay, so if we assumed that force was constant, that'd be an F delta t. Then all we need to know is the amount of time for our collision, and we could get the normal force that acted on the ball. Okay, now there's another thing going on here. We've got, whoops, sorry, wrong lever. All right, so this equation here tells us about maybe friction with the wall there. And so if we needed to, we could also do the same thing. We could say this is some FDT. All right. However, this is a Y, that's a Y, this is an X. And so we could have Fx delta T if it was constant. Okay. Just like so. All right. And then together, if we needed to know what's the total force, okay, we would Pythagorize that. Fx squared plus Fy squared. That would tell us the total force that acted on the ball in order to change the trajectory of the ball. Okay, there we go. Now we're going to look at some more examples. I've got 2 more picked out for you. These are a little bit like the energy ones in the sense that they're not that, there's nothing really tricky here going on. And so you're going to get the hang of this right away. Not much different than how we did all this stuff in physics, okay? See you in the next one.